In this video, we worked some antiderivative problems and evaluate some definite integrals involving a to the x. And we've got one new rule really. The antiderivative of a to the x with respect to x is 1 divided by natural log of a times a to the x plus c. So using that and the fundamental theorem of calculus, we'll be able to evaluate antiderivatives, that plus u-substitution as well, of course. And then fundamental theorem of calculus will allow us to take that and evaluate definite integrals. So I look at this expression and I say, do I have a rule for that? And the answer is no, I don't have a rule for that, but it looks very close to this. If I do a u-substitution, I will be able to evaluate this using that basic rule. So I identify an inside function. My inside function in this case is x, or negative x. So if u is equal to negative x, then this looks like an 8 to the u. And then we're going to have a multiple of du over here. So we'll be able to use that basic rule. So, okay, so I say, do I have a basic rule for that? No, I don't. So let's use u-substitution. Let u be the inside function and then compute du. Du is just the derivative of u with respect to x, which is -1, times dx. And then I say, do I have a -1 dx up there? Well, I don't, but I do have a dx. So if I want to, I can multiply both sides of this by -1. Negative du is equal to dx. And then this integral can be written entirely in terms of u. So we're going to have the integral of 8 raised to the negative x, which is u. And that dx can be replaced by a -1 times du. I'll put the -1 on the far left and the du on the right. And then I say, do I have a rule for that? I said, well, yeah, I do. Sure. I'm just going to use the a to the x rule. We've got a to the u instead of a to the x, but it's basically the same thing. In this case, our a is 8. So the antiderivative of -1 times 8 to the u is -1 divided by natural log of the base, which is 8, times 8 to the u plus c. And then you replace u with whatever it was in terms of x. X was, or u was -1, or excuse me, -1 times x, or negative x. We get -1 divided by natural log of 8 times 8 raised to the negative x plus c. And that's our final answer. If we differentiate using our basic rule for the derivative of a to the x, we get the right thing. The derivative of a to the x is natural log of the base times a to the x. So if I differentiate this, I'll have just this constant times the derivative of 8 to the negative x. So the derivative of 8 to the negative x is 8 to the negative x times the log of 8. So the natural log of 8 and the natural log of 8 in the denominator here will cancel. So we'll have just a coefficient of -1 here. Then we have to multiply by the derivative of the inside with the chain rule, and the derivative of the inside is -1. The -1 from the -1 will be a +1, and the derivative of this turns out to just be 8 to the negative x, and the derivative of the c is 0. So we can check our work if we want to. I just talked through that. We could write out the work if we need to. Now in this one, I've got 2 rules actually. I've got a power rule here and the a to the x rule here. So for this one, we're going to add 1 to the exponent and then divide by the new exponent. Dividing by 5 is the same as multiplying by 1/5. And then on this one, we use the a to the x rule. A is 5. So we have 1 divided by natural log of the base times 5 to the x plus c. And if we differentiate that, we get that back. Actually, I think I really do want to differentiate these. Let's take the derivative. And of course, the derivative of c is 0, so that's going to be gone. Now, when you take the derivative of a constant times a function, you always get the constant times the derivative of the function. So I have -1 divided by natural log of 8. And the derivative of 8 to the negative x requires the chain rule because I've got that negative x inside. So, well, what's the derivative of 8 to some function power? Well, it's going to be natural log of the base times the exact same exponential times the derivative of the inside by the chain rule, and the derivative of negative x is -1. So the natural log of 8 and the natural log of 8 reduce. -1 times -1 is +1. And we just get the 8 to the negative x, which is our original integrand. So we know we did this correctly. Now, similarly, when I take the derivative of this, I should get the original integrand back because the derivative of the antiderivative should be the original function. And of course, the derivative of the plus c is 0. We'll say that what's the derivative of this? Well, the derivative of a constant times x to the 5th is that constant times the derivative of x to the 5th using the power rule. So we'll have 5 times x to the 1 less power. And then we've got a 1 divided by natural log of 5 there. And then we multiply by the derivative of 5 to the x. The derivative of 5 to the x is natural log of the base times 5 to the x. These guys reduce. The 1/5 and the 5 reduce. We end up with x to the 4th plus 5 to the x, which is the original integrand. So we know we did that correctly. All right. So let's check this one out. I say, do I have a rule for that? No. But can I use u-substitution? Yes. Now, whenever you're using u-substitution, you're looking for an inside function. Now, the inside function is usually indicated by parentheses or some kind of grouping symbol. When I look at this, what I see is that x to the 4 or x plus 4 squared inside that power function. I've got 6 to the some function power. It's like the a to the x function, but instead of having an x inside, we've got a more interesting function. Since that's the case, I'm going to use a u-substitution, and I'm going to let my u equal x plus 4 to the 2nd power. So, okay, well, if that's true, then what's du? Well, du requires the chain rule. I've got a function squared. What's the derivative of a function squared? It's 2 times the original function times the derivative of the inside, which is a 1. And then we multiply the derivative of that by dx to get du. And then we say, do I have a 2 times the quantity x plus 4 dx as a part of my integrand? And I don't. I've got an x plus 4 times dx, but I don't have the 2. So I can get rid of the 2 if I just multiply both sides by 1/2. Then I find that x plus 4 dx is 1/2 of du. And so this can be replaced by 1/2 of du. And this can be replaced by an x to the, or 6 to the u. So we can write the integral entirely in terms of u in this way. This is 6 to the u. And the x plus 4 dx is the 1/2 in the du. So I write the 1/2 on the left, the du on the right. And then I say, do I have a rule for that? And I do. Say, okay, well, the base is 6. We're going to have 1/2 times 1 divided by the natural log of the base. It's natural log of 6 times the exact same exponential plus c. And then remember what u is. U is this x plus 4 quantity squared. So we have 1 divided by 2 natural log of 6 times 6 to the u plus c, where u was x plus 4 quantity squared. And if we differentiate that, we should get the original integrand back. But I don't think I'm going to differentiate that this time. We'll have 1 divided by 2 times natural log of 6. Well, actually, I always want to differentiate. That are constant, bring that down. And then you have the derivative of 6 to some power. The derivative of 6 to some power is natural log of 6 times 6 to the exact same power times the derivative of the inside by the chain rule. Well, the derivative of the function squared also requires the chain rule. It's 2 times the original function. You put the original function back inside, and then you multiply by the derivative of the inside, which is just a 1. And then you add the derivative of c, which is 0. So you say, okay, this 2 and that 2 reduce. That natural log of 6 and that natural log of 6 reduce. And I end up with x plus 4 times 6 raised to the x plus 4 quantity squared. Is that the original integrand? It is. So we know we did this correctly. The derivative of the antiderivative is the original function. Our calculations are correct. All right, so now we're here. Now, with this, there are a couple of things you could do. You could use a u-substitution. You could also simplify first. We're going to do a u-substitution either way. But when I see that 3 to the 2x, I really want to simplify. Because I know my exponent properties. If we've got x to the n raised to the m, that's x to the n plus m, or x to the n times m. So when I see that x or 3 to the 2x, my first thought is, let's just take that 3 and square it and then raise that to the x. Because if we do, then we can just call that 9 to the x and everything is much simpler. It just looks simpler. With this, you might think that you have to do a u-substitution twice. First u equals 2x, and then the next time we'd have w equals 3 to the u. Like you could do that. And then after that, you might have b equals 1 plus 3 to the u, or 1 plus w. Like it would just get more and more complicated. You could do 3 substitutions to evaluate this. But if we simplify first, and then let u be the entire denominator, we only have to do 1 substitution. So let's simplify first. 3 to the 2x is actually 9 to the x. And then to make our u substitution as simple as possible, let's let u be that denominator. Then du is the derivative of 1, which is 0, plus the derivative of 9 to the x, which is natural log of 9 times 9 to the x. And then dx is that derivative times dx. I say, do I have that as a factor up here anywhere? I have the 9 to the x dx, but I don't have the natural log of 9. So I can move that to the other side by dividing both sides by natural log of 9 or multiplying by 1 divided by natural log of 9, same thing. And so we've got that there. Then the integral becomes the integral of, I've got that u in the denominator. 9 to the x dx is 1 divided by natural log of 9 times du. And there's an implied 1 in that numerator. We end up with 1 divided by natural log of 9 times the antiderivative of 1 over u du. What's the antiderivative of 1 over u? It's natural log of the absolute value of u plus c. Then you say, I don't want an answer in terms of u, I want an answer in terms of x. So I replace u with 1 plus 9 to the x. Now, it is very tempting to sort of make up a logarithmic rule here, but don't do it. There is a rule, log of a divided by b, that is log of a minus log of b. But there is no rule for log of a divided by log of b. Well, actually, there is one. It's a change of base formula. But I don't know that we want to do that. You might say, what do you mean? Well, if I have log base a of x, that turns out to be natural log of x divided by natural log of a. So we could take this and rewrite it as log base 9 of 1 plus 9 to the x. So that's technically equivalent. And 1 plus 9 to the x is always positive, so we don't really need the absolute value bars. So you could write the answer that way, but I probably wouldn't. I would probably leave it like that. So my thought was initially to try to use that and say, don't ever use that here because it doesn't work. But we do have the change of base formula that would allow us to write the log of a divided by the log of b as this. And again, we don't need the absolute value bars because 1 plus 9 to the x is always greater than or equal to, well, it's always strictly greater than 1. All right. So you could write that if you want to, but you don't have to. I'd stop there. All right. And now I've got one last one like this, as far as our antiderivatives are concerned. You look at your integral, you say, do I have a rule for that? You say, no, I don't have a rule for that. Do I have a rule for that if I use u substitution? I sure do. Look for an inside function. So you might say, oh, the derivative of sine of x is cosine of x, and derivative of cosine of x is negative sine of x, so which one should be my u? Should be the one that's inside another function. So since that's the case, I'm gonna let u equal sine of x. Then du will be the derivative of sine of x, which is cosine of x, times dx. And I actually have that exact factor right there. So this is a 2 to the u times a du. It's very easy to write the integral entirely in terms of u. And you say, do I have a rule for that? Yes. It's 1 divided by natural log of the base times 2 to the u plus c. And then you just replace u with whatever it was in terms of x, which is sine of x. And that's it. That's our final answer. Now we have some other problems that we can work that involve definite integrals. I think we'll work a few of those, and then we'll look at the graphs on Desmos real quick to make sure that we get the same answer using the Fundamental Theorem of Calculus that they do on Desmos. But we'll see that these represent areas, and we'll represent those graphically as well. We'll graph the regions online. All right, so we've got this definite integral, and we can think of it geometrically as representing an area. So let's start by graphing. Y equals 2 to the x has this basic shape. It increases as you go from left to right. It has a y equals 0 as its horizontal asymptote. As x goes to infinity, 2 to the x goes to infinity. When x equals -1, we have, I guess we could make a little chart, right? We're going to have 2 to the -1, which is actually just 1/10. When x equals 0, we have 2 to the 0, which is 1. When x equals 1, we get 2 to the first, which is 2. When x equals 2, we get 2 squared, which is 4. And we're on the interval from -1 to 2. So I wanted to plot those points. There's our graph. And we're interested in this area between x equals -1, x equals +2, the function itself, and the x-axis. Question is, what is that area? Well, it's relatively easy to find. We just compute the antiderivative. It's our a to the x rule, so we get 1 divided by natural log of 2 times 2 to the x, and we evaluate at -1 and 2 and subtract. So 1 divided by natural log of 2 is just a constant, so I'll have that out front, times 2 squared minus 2 to the -1. So it's 1 divided by natural log of 2 times 4 minus 1/2. So that's 8 halves minus 1/2, which is 7 halves. We'll have 7 divided by 2 natural log of 2. That's our exact answer. And we can find the decimal approximation online. We'll do that in a minute. Okay. Now for this one, you might use a u-substitution first. Here I might let u equal x divided by 4 in order to compute the antiderivative. X divided by 4 is the same as 1/4 x, so I'd write that way. Du turns out to be 1/4 dx. And if I want to write my integral in terms of u, I need to write that dx in terms of du. I don't need this 1/4, so I'll multiply both sides by 4. And it turns out that 4 times du is equal to dx. So with that in mind, we can rewrite this integral entirely in terms of u. We've got 3 to the u power. Dx is 4 times du, so I'll put a 4 on the far right and a du on the left. Or I said that the opposite, 4 on the left, du on the right. And then when I evaluate u at -4 and 4, I get -1 and 1. Because really what I'm doing is literally plugging in x equals 4 and x equals -4 to the function 1/4 x to get my new upper bound and my new lower bound. So we're integrating from u equals -1 to u equals +1. Okay, so that is our new integral. So do I have a rule for that? Yes. Let's compute the antiderivative using your basic rules. We'll have 4 times 1 divided by natural log of the base, which is 3, times 3 to the u. And then we evaluate from u equals -1 to 1. So we end up with 4 divided by natural log of 3. That's just a constant, times 3 to the first minus 3 to the -1. And 3 to the -1 is just 1/3. So this is 3/3, or excuse me, not 3/3. 3 divided by 1, which is the same as 9/3, minus 1/3. So it's going to be 8/3. We'll have 32 divided by, that's 8 times 4 is 32 divided by 3 times natural log of 3 as our exact answer. And you might say, okay, well, what does that look like geometrically? Well, 3 to the x divided by 4 is going to look a lot like this. Our base is well, actually, when we substitute in x equals -4, we have 3 to the -1, right? So actually, let's look at that graph. 3 to the -1 is 1/3. And when I substitute in x equals 4, I get 3 to the first here. So it'll just be a 3. And when I substitute x equals 0, I get 3 to the 0, which is 1. So this graph looks a lot like the 3 to the x graph, but we've stretched it by a factor of 4 because we've divided all the x's by 4. We're trying to find that area under the curve. And it turns out that that area is equal to 32 divided by 3 natural log of 3. I don't know what that number is, but we could use a calculator like Desmos to give us a decimal approximation. All right. But 2 more problems. Now on this one, 5 to the x minus 3 to the x, I don't really know what that looks like. But I know that when x equals 0, y equals 5 to the x minus 3 to the x is 5 to the 0 minus 3 to the 0. So it's just going to be 1 minus 1, which is 0. And then when x equals 1, we'll have 5 to the first minus 3 to the 2. Now I don't know what that graph looks like in between, but I know that I'm basically taking 2 curves. One of them that looks like this, and one of them that looks like this. They just have slightly different slopes. They both cross at x equals 0, y equals 1. And then the 5 to the x graph grows faster than the 3 to the x graph. When x equals 1 for this function, we'll have a 5. When x equals 1 for this function, we'll get a 3. But basically, you know, you're taking the difference of those 2 functions. So I'm thinking that when I take the difference of those, it should look roughly like that. I don't know what the rest of the graph looks like, but approximately, I'm looking for an area between x equals 0 and x equals 1 that looks like that. Where that is just part of y equals 5 to the x minus 3 to the x. Okay, well, what is that area? Well, it's very easy to find. Just take the antiderivative term by term. So you get 1 divided by natural log of 5 times 5 to the x for the first term, minus 1 divided by natural log of 3 times 3 to the x for the second term. And then you evaluate from 0 to 1 using the Fundamental Theorem of Calculus. At x equals 1, we're going to have 5 divided by natural log of 5 minus 3 divided by natural log of 3. And then we're subtracting this at x equals, this expression evaluated at x equals 0. Well, 5 to the 0, 3 to the 0 are both 1. So we're subtracting 1 divided by natural log of 5 minus 1 divided by natural log of 3. So I end up with 5 over natural log of 5 minus 1 over natural log of 5. That's going to be 4 divided by natural log of 5. Then I have negative 3 over natural log of 5 minus a negative 1 over natural log of 3. I said natural log of 5 and natural log of 3. But these are like terms. I have a negative 3 and a plus 1 there. So it's going to be a negative 2 over natural log of 3. I don't actually know what that number is. And I know 5 to the x is greater than 3 to the x. Just because the graphs are going to look roughly like that. So I expect this to be some small positive number. That positive number is going to be that area. All right, now in this one, we're asked to find the area of the region bounded by y equals 3 times cosine of x times sine of x, y equals 0, x equals 0, and x equals pi. So, oh goodness, what does that look like? If I evaluate this function at 0, I'm going to have 3 times cosine of 0 times sine of 0, which is just 0. Okay. And then I'm on the interval from 0 to pi. I'm on the interval from 0 to pi. Cosine will be 0, but we're taking 3 and we're raising it to that power at the cosine 0 at pi over 2. But sine is equal to 0 at pi as well. So if I evaluate this at pi, I get 3 times cosine of pi times sine of pi. So that's 3 to the negative 1 times 0. So I get 0 there. But my sine values are all between 0 and 1 on the interval from 0 to pi, because we know that sine looks like this. So I'm taking this 3 to the cosine of x, where cosine is between negative 1 and 1, and I'm multiplying it by a number between 0 and 1. So the values of the 3 function, the 3 raised to that power, are all going to be between 1/3 and 3. And then we're taking those numbers between 1/3 and 3, and we're multiplying them by a fraction. So I'm expecting just sort of a reasonable range of y values that are all positive. And we want the function, we want the area of the region bounded by the graph of this function, which I don't know what it looks like. Y equals 0, which is the x-axis. That's y equals 0, x equals 0, which I said the x-axis. Y equals 0 is the x-axis. X equals 0 is the y-axis, and then we want x equals pi. Say, okay, well, what does this graph look like? I don't really know, but I know it's a positive. It's going to be positive, and it's going to, the function's going to lie between 0 and pi, and I'm expecting something sort of sinusoidal, but then I'm multiplying by this exponential factor. So I'm going to get something in here that looks like that approximately. I know it starts at 0 and ends at 0, and the function is continuous because it's a composition of continuous functions multiplied by another sinusoidal function that's continuous. So I know it's continuous and it starts here and ends here and then it's positive. So I'm going to say roughly it looks something like this. I don't actually know, but I know that I'm looking for the area between that function this curve, and this curve, and I know that the function is positive there. Because I know that this is a number between 1/3 and 3 times a positive number. So we're gonna have something that looks like this. And that's the area that we're looking for. We say, okay, well, if that's the area that we're looking for, approximately, what is the integral going to be? Well, it's going to be the integral from this x value to this x value, so 0 to pi of this 3 to the cosine of x times sine of x. You say, do I have a rule for that? No, but can I use u-substitution? Yes. So we look for an inside function. The cosine function is inside that 3 to the x function, so we'll let u equal the cosine function. Then we say, well, what is du in that case? Well, du is the derivative of cosine, which is negative sine, times dx. And we say, do I have a negative sine of x dx? Say, well, I have a sine of x dx, not the negative. So if I multiply both sides by -1, I get sine of x dx is negative du, and I can rewrite this as negative du. And again, remember, the goal is whenever you're doing a u-substitution, you want to write everything in terms of u. Every single piece is replaced with a function involving u, including the bounds. So you say, okay, well, what is this integral in terms of u? The 3 is still there. We're raising that to the cosine of x power. What's cosine in terms of u? It's just u. And then you're multiplying by sine of x dx. Well, what's sine of x dx in terms of u? It's -1 times du. So we put the negative out there and the du to the far right. And you say, okay, well, what is u evaluated at 0 and pi? Well, it's relatively easy to find. You just plug in 0 and pi to that function u to get our new bounds. When we evaluate u at pi, we get u equals cosine of pi, which is -1. That's our new upper bound because pi was our upper bound. Then we evaluate u at 0. We get cosine of 0, which is +1. Since 0 was our lower bound, +1 is our lower bound. Now, some students will say, I don't like that because 1 is greater than -1. And shouldn't the lower number be in the bottom instead of the top? You say, well, yeah, if you prefer to have the -1 here rather than the +1 here, you can multiply by -1 and flip those bounds. It's totally fine. You can do that. So this integral is equal to this integral. And you say, do I have a rule for that? Yes. That's 1 divided by natural log of 3. Well, excuse me, we do have a rule for that. So we applied the antiderivative rule. We have got 1 divided by natural log of 3 times 3 to the u. And we evaluate from -1 to 1. Those are u values. So you just plug those in. So that's 1 over natural log of 3 times 3 to the first minus 3 to the -1. So that's going to be 9/3 minus 1/3. That's 8/3 times that 1 divided by natural log of 3. So we're going to have 8 divided by 3 natural log of 3 as our answer. And that's going to be some number. It's going to be a positive number. And it's going to represent an area that looks like this. I don't actually know what that curve looks like, but I know that the function is positive and it's equal to 0 at 0 and pi. So I'm saying roughly it looks like that, and that picture is enough to get me this definite integral. This is sort of a cartoon of y equals 3 sine of x to the times cosine of x. If I want a better graph for 3 sine of x times cosine of x, we could use our curve sketching techniques. We could compute y prime, y double prime, think about relative extrema. We can also just use Desmos.com if we want to visualize it relatively quickly. And we will do that in just a moment. So we were able to compute all of those definite integrals. We got the final answers in terms of logarithms. Let's look at the numerical approximations of those and then the corresponding regions. All right, so we looked at the integral from -1 to 2 of 2 to the x dx. We found an exact answer of 7 divided by 2 times the natural log of 2. We see that Desmos' calculation and our exact answer have the same decimal approximation. This is a graph of the region. And we can also evaluate the integral using the Fundamental Theorem of Calculus, which we did on paper. We found the antiderivative, we plugged in the bounds and subtracted, and we get the same answer that way. So that was our first example. This is how we visualize it. Here's a little code for visualization. And then we've got something similar here. Our function is f of x equals 3 to the x divided by 4. It looks a lot like 3 to the x, but since the x is divided by 4, we've just stretched the graph 4 units to the right, or 4 units in a horizontal direction. Everything is multiplied by a factor of 4 in the horizontal direction. When we evaluate, or we were looking for the integral between -4 and 4 of 3 raised to the x divided by 4, and we get that 9.709. Our exact answer was 32 divided by 3 natural log of 3. And that's the same, it has the same decimal approximation as the decimal approximation of the definite integral using Desmos. We can visualize the area this way. We can also see that this is that 3 to the x graph stretched by a factor of 4. If we look at the 3 to the x graph, and you look at that interval for 3 to the x between -1 and 1. I just want to show you. You can see that the height here at -1 is the same as the height here at -4. And then the height at 1 here is the same as the height at 4 there. So we've stretched everything for horizontally by a factor of 4. But otherwise, the graphs basically look the same. It's just wider. We got our exact answer that way. We actually did a u-substitution. We wrote the integral in terms of u, and you see the integral in terms of u, it has the same value. And when we used the u-substitution, we computed an antiderivative in terms of u, and evaluated u at the various bounds and subtracted, and we get the same answer. Usually I don't use Desmos for that, but it's a good way to check your work. I would encourage all of my students to visualize regions, try to do it on paper, but then also visualize it graphically on desmos.com. Make sure that you understand what the graph actually looks like, and then compare your answers to those calculated by the graphing calculator. Now this one was a little bit more interesting. We had 5 to the x minus 3 to the x as our integrand. Now 5 to the x looks like that. It's that teal graph. And then 3 to the x looks like that. And we're only interested in the function between 0 and 1. Now on the interval from 0 to 1, we can see that the 5 to the x graph is higher. It has larger y values than the 3 to the x graph. So on that interval, when we subtract, we get values between 0 and 2. The functions are equal to each other at x equals 0. So we get a 1 minus 1, which is 0 there. And at x equals 1, we get a 5 minus a 3, which is a 2. And then for all of those x values in between, we're just taking the difference between those y values to get these y values. Now, if I want to graph the function 5 to the x minus 3 to the x, I can. And we see that that function is actually negative to the left of 0 because our 5 to the x graph is actually larger than the 3 to the x graph. That's because we're taking 5 and raising it to a negative power, and you want to compare that to 3 raised to a negative power. Like 1/5 is smaller than 1/3. So I think I may have said that backwards earlier. The 3 to the x graph, that's the orange graph, is actually larger, has larger y values than the 5 to the x graph over here. Because if you take something and divide it into fifths, that's those pieces are smaller than if you divide it into thirds. So we get negative values for the y values of 5 to the x minus 3 to the x to the left of 0, and then positive values to the right. But again, we're only interested in the interval from 0 to 1. So we say, okay, what is the region that we're interested in finding the area of? Well, it's the set of all y values where y is between 0 and 5 to the x minus 3 to the x, and x is between 0 and 1. So that's the code for that. And that is represented, that area is represented by this definite integral. And we see that that's approximately 0.665. Now we just used the fundamental theorem to calculate the exact answer. We evaluated the antiderivative, we plugged in 1 and 0, and we subtracted. And this is our exact answer. After simplification, we see our exact answer simplifies to the same decimal approximation as that given by Desmos. You can also use Desmos to do that calculation. So you can type in that antiderivative and plug in 1 and 0 and subtract, and you see that you get the same value. So I think that's kind of cool, kind of interesting to think about. Like, I know what 5 to the x looks like, and I know what 3 to the x looks like, but what would the difference look like? This is that purple graph is what the difference looks like. And then the last one involved this 3 to the cosine of x times sine of x. It's actually a really cool curve. Lots of hills and valleys. So you've got, you can see that it's periodic. Looks like it's periodic with a period of 2 pi, which makes sense because cosine has period of 2 pi and so does sine. But we also see, you can see some relative extrema. I've got an extreme value there and there. I've got a point of inflection there and there. And then I think I have a flat spot right there. Maybe I'm wrong. I'm actually not sure what the derivative is there. But well, maybe it's not flat. Maybe that derivative is like a small negative number. But there's some interesting possibilities for curve sketching with this particular function. But we weren't asked about curve sketching. We were asked for the integral, or we were asked for the area between this function, y equals 0, x equals 0, and x equals pi. So let's say I don't actually know what that looks like. If I don't know what that looks like, I would graph all of the boundary curves, those 4 curves, y equals 0, x equals 0, x equals pi, and then y equals this 3 raised to the cosine of x times sine of x. And then say, okay, what region is actually bounded by all 4 of those curves at the same time? Now, since I didn't actually know what 3 raised to the cosine of x times sine of x looked like, I just guessed. And I said, well, the function is definitely positive on that interval. And I'm going to say it looks approximately like this. But yeah, I didn't know about these sort of details. I didn't know where the relative extrema was, where that relative maximum was. I didn't know where the second derivative was 0. So I didn't know where my point of inflection was, where it changes from concave downward to concave upward. But I had enough information to know that this was the definite integral we were looking for. So we said, this is our definite integral. We used a u-substitution to get an exact answer of 8 divided by 3 times the natural log of 3. And the decimal approximation of our exact answer is the same as the decimal approximation of the integral. Now, when we did the u-substitution, we let u equal cosine of x, and the integral became this integral in terms of u. After we computed the antiderivative, we got this function, and if we evaluate the antiderivative at the endpoints and subtract, we get the same value. And all of those values are the same, so we get that 2.427 approximately as the area under the curve. But again, if I don't know what the region looks like, I usually graph those boundary curves. So this is what the problem statement originally said. And I said, okay, let's graph y equals 0. That's that green line. X equals 0. That's the white line. So y equals 0, we know is the x-axis. X equals 0, we know is the y-axis. I think I want them all to be the same color. And then I needed x equals pi as well. And then I wanted f of x. And so when I didn't know what f of x looked like, but I knew that my f of x function was 0 at 0 and pi. And then I could infer that because sine is always positive on the interval from 0 to pi, and cosine of x is between -1 and 1, I knew I was taking a number between 1/3 and 3 and multiplying it by a number between -1 and 1. And so that gave me all of these values. So I knew that my values were going to be positive, so I knew the curve was going to be above the x-axis. That was how I knew what the definite integral should be, even though I didn't know what that curve looked like. But once we had our graphing calculator out, we could find that curve. We could shade the region. We want all the y values between 0 and f of x on the interval from x equals 0 to x equals pi. And then we were able to set up and solve the definite integral using the substitution. All right, that's it.